All right, in this video, this is the last topic that we're going to talk about for BC Calculus. And it's topic 9.9. It's finding the area of a region bounded by two polar curves. So let's get right into it. It says the area bounded by a polar curve, we know from the last lesson, the area is equal to 1/2 the integral from alpha to beta of our radius squared d theta, because the radius is a function in terms of theta. So we plug that in. All right, so things to watch out for, things that make things easier, is using symmetry. And then a big part of today's lesson is going to be finding points of intersection. So number one, and it says find the area of the region common to the polar curve r is equal to 4 cosine theta and r is equal to 2 sine theta. So this one, it is calculator active. So we could just plug this into our calculator and know what it looks like, but I'm going to just kind of refresh our memory. I think it's helpful as much as possible to be plugging in thetas and understanding what that means. So if I plug in theta is 0, and this one is going to be for, let me fix this. When r is equal to 4 cosine theta, I have theta and r. If I plug in 0, I get, cosine of 0 is just 1, so I get 4. If I was to plug in, let's see, maybe pi over 2. Cosine of pi over 2 is 0, and then 0 times 4 would be 0, so my radius would be 0. And by now, hopefully we kind of remember, this graph, it's going to start out when the theta is 0, my radius is 4. So 1, 2, 3, 4. And at pi over 2 radians, my radius is just 0. And this is actually going to be a circle with radius 2. So it's going to look up like this. Okay, that's terrible. Not too bad. All right, so radius 2 circle, and I want you to graph this also. So if you have your calculator, you can graph this. R is equal to 2 sine theta. Hopefully we kind of remember it's a circle above the x-axis. But we're going to plug in some numbers and just double check. Okay, if I plug in 0, 2 times sine of 0 is just 0, so that'd be what, 0? So the radius is 0 at theta 0. But if I plug in pi over 2, sine of pi over 2 is 1. Then 1 times 2 would be 2. So I get that point. So this one is a circle with radius 1. And it looks kind of like that. And again, if you draw this in your calculator or plot this, make sure you're in polar mode, plot that. You see this picture. Okay. So from here, what I'm trying to do in this lesson is find the area. So in this one, find the region common. So find this area right here. So I'm going to draw and just try to get some background. So if I'm looking at the blue, if I integrate from 0 all the way to pi over 2, I'm adding up all that area, right? But I don't quite want all of that. I don't want this part over here where it's not overlapping. And then if I go back, okay, you gotta do all this. If I integrated the red one, it would be like starting at 0, it'd be really small, and they start to get bigger and be all of that. So what I'm gonna try to do, oh no, is I wanna integrate, oops, and I want to zoom in right here. So what I want to do here is I want to add up all the radiuses. At first, when theta is 0, I go out and I touch the red one, and I touch the red one, I touch the red one, touch the red one, I touch the red one. That radius is coming from the red function. Then it's the intersection point, and then my radius is coming from the blue function. So what I'm trying to do is I'm trying to add up all those radius is. Those would be like my little sectors that I'm creating. So my equation, the area is equal to 1/2, and it's going to be my theta. I'm looking at the red one first, because at first my radius comes from the red function, and it starts at 0 when theta is 0, and then it goes until that intersection theta. I got to find out what that is, and then I'll use the blue function to find the radius from that region, for those regions. All right, so I need to find that limit of integration, and I'll find that in a second, but I'm getting that from the red one, and the red one was the 2 sine theta squared d theta. I'm going to add that to 1/2 the integral from question mark. I get my radiuses starting at theta, where they intersect, all the way to pi over 2. And that one is going to be from the blue functions where I get my radius. The blue function was 4 cosine of theta squared d theta. All right, so the next tricky part on this one is going to be, what is that theta where they intersect? I clearly know it's somewhere between 0 and pi over 2. So what I do is I said, okay, the radius is going to be the same at that intersection point. So I'm going to say 4 cosine of theta is equal to 2 sine theta. Divide both sides by 2. I get 2 cosine theta is equal to sine theta. Divide by cosine, I get sine theta over cosine theta. Okay, now this is kind of a tricky one. I know sine over cosine is equal to tangent. So I don't know the theta where tangent is 2, so this is where the calculator would come into handy. I would say tangent inverse of 2, plug that to the calculator, and it gets you theta is equal to 1.107. So this is absolutely calculator active, calculator necessary to find that theta for when they intersect. So let me erase this again. Erase all these little thetas. Okay. No. Don't want to erase that. Okay. Nope. Okay. Might not be able to get all of them. Nope. Okay. So when theta is 0, I get these little tiny radiuses. And as theta is increasing, the radius comes from the red function. And as I'm adding them up, this is what that first integral gives me. It's adding up all those sectors. And then at that intersection point theta, here's a theta right here. This is theta is equal to 1.107. So when theta is 1.107, they intersect, and then now if I integrate, I would use a different function to get my radius. I get that blue one, and as I add up all those infinite number of segments, I get that area. All right, so if I plug this into my calculator, so I'm going to erase this. This is this limits of integration. Now I know they're 1.107. Plug this into the calculator, and I get 0.962. All right, so the key part on this type of question is finding that intersection point. So this one, it's going to take a little second to visualize that, but as soon as it clicks, it's nice, but until it clicks, it can be kind of frustrating. So hopefully this video helped. I'll do the next question in the next video. Thanks for watching.